In this video, we'll go over how to make a physics-based character controller that can navigate the miniature solar system I showed you how to make in part 1. Okay, so we have our planets set up, so the next thing to do is, of course, to add our player character. For that, I'm going to add a new child node, and this will be a rigid body 3D. We will call this the player, and actually, let's right-click on this, and go down to Save Branch as Scene, and then click to open it in the editor, and we will edit our player character here instead. So the first thing that any good player character needs is a mesh instance 3D with a new capsule mesh in it. And I'm going to turn the preview sunlight back on in this scene. Next up, we want a collision shape 3D. I'm going to use a cylinder shape for this so that there's a flat surface at the bottom. Next, we're going to set up our camera. So first we're going to have a node 3D, which is going to be our camera pivot. And then underneath this camera pivot, we'll put our actual camera 3D node. And we'll take this camera pivot and just move it upwards a bit so that it's at the player's head. While we're exploring our solar system, we're going to want to be able to actually see what we're doing when we're on the dark side of the moon or whatever. So we will add another node underneath our camera 3D, which will be a spotlight 3D. Let's extend the range out a bunch, say 50. So now we have a flashlight. And the last thing we're going to want on our player is a way to tell that the player is standing on the ground. And for that, we're going to add a raycast 3D, which will cast to -1.4 on the Y. So you can see this blue line coming out of the bottom of the player. That's the raycast. And it's actually coming out of the bottom, so it will actually make contact with the ground, and we'll use that to know if we're on the ground or not. And to make that pretty clear, we're going to rename this raycast to groundcast. With all that out of the way, we can start working on our script. So C# script inherits rigid body 3D player.cs. Okay, so I'm going to clear out all the boilerplate for now. We're going to start with our exports. We're going to define a new export category, and we'll call this nodes. This is going to be all those nodes that we just created. So the first one we have is a private camera 3D camera. We also have the node 3D camera pivot, and lastly we have the raycast 3D, which was our ground raycast. What we can do after this is, so how this raycast is going to work is we're going to use it, one, to tell if the player is standing on the ground. So for that, we're going to define a property called isGrounded that will just give us the value of groundcast.isColliding. And I just like doing it this way to sort of, make it a bit more clear what we're doing. We could write, groundcast.isColliding every single time we want to check if we're standing on the ground, but I feel like just calling isGrounded is like way more obvious to you as you're writing your code what that does. So that's why I like to do that. Similarly, we are going to have a public planet that we're going to call ground, and that is going to return groundcast.getCollider. So this is the physics body that it's colliding with, and we're going to cast that to being a planet. So again, we could write this out every time we want to do it, but I think it's a lot more obvious if we just have a thing called ground that is a planet. That it'd be a lot easier to figure out what that means. Okay, next we're going to do another export category, and this is going to be our settings. First setting we're going to put will be private float mouse sensitivity, which will start at 0.3. Related to this mouse sensitivity, we are going to store a vector 2 that I'm calling mouse delta. So this is going to track between physics frames the movement of your mouse, left and right and up and down, because we're then going to use that mouse movement to actually move the player in the way they're looking. You'll see in a bit why it's relevant to keep tracking this. And related to that, we're going to store a float called camera x rotation. And this is the rotation around the x-axis, which is sort of like the left-right axis. So it's looking up and down. So it's a bit confusing, right? Because that's the y position of the mouse, but it's the rotation around the x-axis. So don't get confused by that. Next, still related to our settings, but no longer related to the mouse, we are going to define thrust. This is going to be, the strength of our jetpack as we're flying around in space, or just our movement on the ground is also going to be done as a thrust. We are also going to have the auto orient speed, which is set as 0.5. And this is going to be, if you're familiar with something like Outer Wilds, where when you get close to a planet, it sort of starts turning your player so that their feet face towards the ground. This is the parameter that will control how quickly that happens. And lastly, the private float jump impulse. So this last one is just when you press the spacebar, it'll apply an impulse equal to that. So let's start with the physics process method. So in this method, we are going to do a few things, right? We're going to consider the movement of the player, so WASD. We're also going to use shift and control for going up and down with our jetpack. We're going to consider, where's the player looking, and then if they're approaching a planet, we're going to orient them so that their feet face the ground. But also, if they're in, far from a planet out in space, we also want to consider sort of differently how they're looking around. Say if you look down at your feet on the ground, you don't want your entire body to spin around so your face is lying down on the ground. But when you're in space, we want you to be able to fully, flip 360 degrees in any direction. So quite a few things we're going to have to consider in this physics process method. And for that, I'm going to write some helper methods. So the first one will be process movement inputs, and we'll pass through our delta time just in case we need that. We are also going to consider our look inputs. Again, we'll keep the delta time just in case we need it. And then for rotating the player around automatically, we are going to have this process auto orientation method. And then back in our physics process method, we will call each one of these. So we call the movement inputs, we call the look inputs, and we call the auto orientation. So first up, in movement inputs, we want to check, the keyboard inputs. Of course, those don't exist yet. We haven't set them up. So we'll go back into our project. Let's just save the player scene. Save the solar system as well now that we've added the player to it, and perhaps we'll take the player outside of the interior of the sun. That will probably help when we go to play the game. Now we just go to project settings, input map, and now I'm going to add in all the different inputs. Okay, so I just quickly added in all of our inputs. So you can see we use WASD for forward, backwards, left, and right. We're using shift and control to move up and down. For this input here that I'm calling map, this is basically going to be, if you remember before when we played the game, we just saw a perspective of the solar system from the top down. We're going to make it so that pressing escape toggles us between our player view and that sort of map view, and also when you're in the map it'll free your mouse so you can quit the game. Spacebar to jump, and R to rotate. So what this is going to be is that when you're in space, while holding down R, you'll rotate around your forward Z-axis instead of rotating around, you know, the Y-axis when you look left and right, and the X-axis when you look up and down. So by holding down R, we're going to be able to move on all three axes while we're in space. Alright, so we go back to our script and process movement inputs. So when we start out, our movement vector is going to be 0. The forward direction we can get by doing global transform.basis.z, and by Godot convention, the forward direction is the negative z direction. Similarly, for left, that's going to be the negative x direction, whereas up is the positive y direction. Now when we check each of our actions, so next should be input.isActionPressed forward, then we do movement plus equals forward. Similarly for backward, it's instead going to be movement minus equals forward. For left, we're going to do movement plus equals left. For right, movement minus equals left. For up, movement plus equals up. And lastly, down, movement minus equals down. Now, if our movement vector is not still 0, then we will call apply central force, and we will take our thrust that we defined and multiply that by the normalized movement vector. And the reason why you normalize this is, of course, if you're pressing forward and say left at the same time, that's sort of 1 in the forward direction and 1 in the left direction, which adds up to be greater than 1 total, so you move faster along a diagonal than if you were just moving in a single direction. So we normalize it to keep that at 1. And now here we will also do if we are grounded, and if input.isAction just released jump, we will apply a central impulse, which will be our jump impulse times the up direction. So of course you press space, you will get this instantaneous impulse that will push you upwards. So that's it for the movement inputs method for now. Next for our look inputs. So first we're going to track the this is the movement around the x-axis, so the rotation up and down. And as I was saying before, that's kind of confusing because that's mouse delta.y, and we'll multiply that by our mouse sensitivity. Because remember, moving your mouse up and down is rotating your camera around the x-axis. Similarly, delta y, we will do mouse delta dot x times mouse sensitivity. Now if input.isAction pressed rotate, this is what I was saying about the purpose of that input, is if we're going to rotate around, we're going to take our camera pivot, its global transform, and it's Z. So this is sort of, the forward, or I guess technically it's the backward, but the axis in which we are looking, the direction that we're looking in, we're going to rotate around that by, and now our, as you could just tweak this value to make sense with this being radians, but the 0.3 that I chose makes it work well with this as degrees. So we're going to convert our delta y from degrees to radians because rotate expects an angle in radians. And that's going to rotate us around the forward vector. Otherwise, we're going to do rotate object local. So this rotates us around, as the name suggests, a local vector. So if I put in vector3.up, that's not, just the y-axis of the entire scene. That's specifically, up from the perspective of the player. And again, we convert from degrees to radians, and we're going to take delta y. So essentially, in this case, we're rotating around the vector, the direction in which we're looking, whereas this one, we're turning left and right. Next, we're specifically going to consider how we're looking up and down. And for this, we're basically checking, if we add this new change in the x rotation angle, are we going to go outside the range of 90 degrees up and 90 degrees down? Because if we didn't do this, then you could potentially, look up and then keep looking up until you're looking behind you. So we don't want that. So only if we're actually within the range of 90 to negative 90 do we want to actually rotate. And for this, we're going to rotate our camera pivot around the x-axis by our delta x. And again, we're converting from degrees to radians. And we're just going to add this change in the angle to this camera x rotation variable where we're keeping track of it, and we're just keeping track of it specifically to be able to make this check to make sure that we're still in the range. Now for this auto orientation, a thing we're going to want to do in here is, as I was saying before, this is going to behave differently if you're close to a planet or if you're far off away from a planet. But to do that, how do we determine whether or not we're close to a planet or if we're in, deep space? So to do that, we're going to head back to our physics process method. And what we're going to do here is we're going to look through all the different planets in the solar system, and we're going to see how close we are to each one and how much their gravity is affecting us. So for that, we're first going to define this variable closest force magnitude, and that's going to get updated as we loop through all of the planets in the solar system. So for each planet in solar system.instance.planets, and that's why we defined that static instance variable in the solar system script, so we could use it here. And then we're going to get the force that planet would be applying to us at our global position. Now, of course, this is an acceleration, so to convert that to a force, we just multiply that by our mass, which is a rigid body 3D variable. Now, for every planet in the solar system, we are actually going to apply that force to our player character. Unlike the planets, which are only affected gravitationally by whatever they're orbiting, the player is affected by every single planet in the solar system. Let's also record the closest force. So what I mean by closest force is it's, the closest planet to us, what force is it exerting on us, right? So be a bit wordy to write that all down in here, so we'll just call it closest force. Now in here, we can say, so when we're in the solar system, the thing about gravity is that it goes on infinitely. Like, you could be, 10 light years away from the sun, and the sun would still be affecting you gravitationally. It would just be affecting you in the most, infinitesimally small way, right? But it is technically, this infinite distance that gravity works over. So if we were to just check, is any force being applied to us at all, the answer would always be yes. Just, be a tiny, tiny amount possibly, but yes. So what we're going to do is we're going to ignore planets that we're far away from. So we're going to get the global position of the planet, and we will find its distance to us. And if that distance is less than 2 times the surface radius of the planet, then we will actually consider ourselves as being close to it. Otherwise, we'll ignore it and say that we're, effectively in zero gravity. So we're close enough to a planet. Now we're going to check what force is it exerting on us. And if the magnitude of that force is greater than the closest force magnitude that we had previously checked, then we will set that closest force magnitude value to be equal to the magnitude that we just checked, and we will say that the closest force we are experiencing is that force. And this is essentially going to be, what direction is down, right? Because this is saying where gravity is pulling us currently. So we don't want that to just be a local variable here. We actually want to define it sort of globally. So we'll put that up here. We will say private vector3 closest force, and we will just use that instead of this variable. Okay. So now we go back down to our auto orientation method. And we can now say, okay, are we in zero gravity? And that will be the case when closest force is equal to 0. So first, we're going to consider, okay, we're in zero gravity. In this case, we want to say that when the player looks down or up, we're going to rotate their entire body to face that direction. So if you look 90 degrees upwards and then you press forwards, if you're standing on the ground, you're just going to keep moving, in that original direction, parallel to the ground, right? You're not going to suddenly start flying up off the ground. You wouldn't expect that to happen in a regular game. However, when you're out in deep space in zero gravity, when you sort of flip yourself around and look up, you do want to start going in that direction. So that's sort of what we're going to do here. We're going to rotate the player so that their body is actually facing upwards. So to do that, we're going to lerp between 0 to negative camera X rotation. And the amount that we're going to do that at is our auto orientation speed times the time step. So this value here is sort of going to smoothly approach the exact opposite of our up and down camera rotation. And we're going to use that to cancel out that rotation by moving the player around. So first we're going to add that value to our camera X rotation. So remember that that's a negative value. So if the player looked all the way up, it's going to make the player start looking slowly back down to look forward. And to have it actually rotate the player's camera like that, we are going to apply that rotation to the camera pivot, but then we're also going to rotate the player's entire body by the X direction according to the camera pivot, and we're going to do that by that angle dx. So you can see that the camera turns downwards by dx, but then the player's entire body turns upwards by dx, sort of canceling it out, but actually rotating the player body in the right direction. I'll do like a demonstration in-game with a third-person camera so we can kind of see how that actually looks later on. Now otherwise, if we're not in 0G, then, well, we're close to a planet. So we want to turn our feet to face towards the ground. To do that, we want to say, you know, what direction is up? And up is going to be the opposite of the gravity we're experiencing. So gravity is pulling you down towards the ground, so up is in the opposite direction. Now, I suppose this should be like orientation, rotation. This is going to be, you know, what our player's rotation should be in order to have their up direction be up. So to do that, we're going to get a new quaternion. And if you give a quaternion two, that should be global transform, two vectors. So if we give it our local y vector and then the up direction, what it returns is an angle that will take you from this direction to that direction. So we want this rotation to transform us from up being our current up direction to being this desired up direction that is away from the gravitational force that we're feeling. And then we apply that rotation to our current rotation to get our desired rotation. Now, if we are standing on the ground, we want to essentially automatically, immediately get this rotation. We always want to be, you know, standing up straight when we're on the ground. However, when we're, you know, in the air around a planet, we want to smoothly move to this rotation. So we're going to check, are we grounded? If so, we directly set our global rotation to be our orientation rotation, and we're going to normalize that. It's always good to normalize your quaternions, else the game might complain. And Godot's global rotation is as a vector 3. This is as they say, y, x, z Euler angles. So we can take our quaternion and just go get Euler, and give us those. Otherwise, our rotation is going to be our current rotation, so global transform.basis.get rotation quaternion, and we are going to spherically, linearly interpolate from that to our desired orientation rotation, which again we're going to normalize, and we're going to move towards that by our auto orient speed times the delta time. So whereas here we directly set it to the desired value, here we're smoothly approaching that desired value, and then we are going to set our global rotation equal to that quaternion, and once again we have to get its Euler angles. Whoops, not global rotate, global rotation. Okay, so now the last thing for us to do here is, of course, up here in process look inputs we're using mouse delta, but we haven't actually set that value yet. And the reason why we're even tracking that separately is because that value is going to get set in public override void input. And instead of doing at event, I'm just going to rename that to be E to get rid of the at. Now if our event E is an input event mouse motion, this means, of course, that we just moved our mouse. And we will cast, we'll write it like this, because now this mouse motion variable is just equal to E when cast to be an input event mouse motion. And then down in here we can just go mouse delta plus equals mouse motion dot relative. And this is because this input method isn't necessarily being called at the same speed as our physics process method. So we want to be able to make sure that, you know, we get all the mouse movements, we add them all up before applying them up here in the physics process. Although now currently, right, these movements will keep getting added and added and added. There's nothing that's going to reset them. So if we go in here to process look inputs, so this is where we end up using the mouse delta, and that is being called up here in physics process. So just at the end of this method, once it's done using those mouse movements, we're just going to reset them back to 0. Not vector 3.0, but vector 2.0. Let's define our ready method. So what I was saying before about us having a map view, right, where we can alternate between viewing the map and seeing out of the player's eyes. So for that, we're going to define a method called showMap that will take in, you know, should we be in the map or not, and we will track if we are in the map or not with a boolean called inMap. So in the showMap method, we will set inMap equal to inMap. If we are in the map, we are going to take our mouse mode and we will set it to input.mouseModeEnum.visible. So when we press escape, we're going to be able to see our mouse, and we are going to disable the player's camera. Then by default, since the map camera is the only other camera, we're going to end up using that one instead. If we are not in the map, then we are going to set our mouse mode to input.mouseModeEnum.captured. So this is going to hide our mouse and lock it to the center of our screen. And we are going to activate our player camera. With that set up, when we start the game, we're going to say showMap false, which will make us start playing as the player character. And we can check in our process method if input.isAction just released map, and if we have just hit the map button, then we'll do showMap with the opposite of our current, you know, map state. So that'll just always make sure that it flips between showing the map and not showing the map every time we press escape. Okay, so I've left a few things out of here so far just because I want to sort of demonstrate, you know, why we're going to need those things. So I'll go back to our game scene and we'll build it, and let's see if running this works. And actually, I've just remembered that it won't. And you can see all the errors getting thrown. It's because I always forget to set my exported values. So we just built, we can set our exports. So drag and drop our camera, drag and drop our camera pivot, and drag and drop our ground raycast. And we'll save the scene and start the game again. Okay, so you can see that I'm sort of falling down out of the solar system, and that's because I forgot something very important. Go into Project Settings, go to General, you just search for Physics, go under Physics 3D, and you can see that, you know, by default, the game applies gravity going downwards. Of course, we're in space, there's no such thing as down, so we'll set the default gravity vector to 0, set the default gravity to 0, Similarly, in space, here we have default linear damp, default angular damp. So these are sort of, like air resistance, friction type stuff. We're in space. There's no air resistance. So we'll also set these to 0. If we launch our game again, so I mean, you can't tell, but actually my controls are backwards. My mouse looking up and down and left and right is backwards. So we'll just quit out of that. Go back into our player script, and at the look inputs, we're going to change this to negative mouse delta dot y, negative mouse delta dot x. Now we go back into the game, and there you go. Left and right, I'm looking left and right. Up and down, I'm looking up and down. And actually, the rotation is pretty broken. To investigate why that is the case, I'm going to go in here, take my camera, and just pull it out the back of my head. And just like that, I'm going to be able to play in third person. One thing I forgot to do here in auto orientation is to fix our angular velocity to be 0. We don't want the player to be spinning around outside of our control. So set their angular velocity to be 0. Similarly, we're going to set the angular damp to be 10, just to really ingrain in there that we are not going to be rotating. Another thing I'm going to do is, with our exported settings here, let's bump our thrust up to 10. I want to really be able to move. And let's change this auto orient speed to 2. We saw that the player was rotating a bit too slowly when we got to the Earth. So now with that, good, I actually have enough thrust to get to the Earth. See, we've pretty quickly turned around to stand on the surface of the Earth. And now that we're damping our angular velocity, you can see we're not spinning weirdly out of control like we were before. However, if you pay attention here, you can see that although I'm standing still on the planet, the ground is rotating underneath me. Now this is because we have no angular velocity. However, the surface of the planet does. So, to fix that, we go back into our script. And so here we've set the angular velocity to 0. That is good in most cases. However, when we are standing on the ground, what we're going to do is we're going to set our angular velocity to be equal to the constant angular velocity of the ground, and we are going to project that vector onto our up direction. Now, this came to me in a dream. I don't know why this works, but it makes sense, and just trust it. Cool. And we're also going to set our angular damping to 0. We want to make sure that... I think this might be unnecessary. I'm not sure. This was giving me a lot of headaches before, so I was just like, you know what? Give me as much damping as possible. But here, when we're purposefully setting it to be equal to something, we're like, no damping. Don't mess with the value that I set. Now launching the game again, we fly over to the Earth. Let's head back down to Australia. And now you can see that the ground underneath me is not rotating anymore. However, if you look closely, you can see we're kind of drifting. See, like the player's slowly shifting to the right. And that's because, there's so much going on in the solar system. There's all these, every planet is pulling on the player gravitationally. The ground is spinning underneath us. It's not ideal for us to be drifting like that. So we're going to put it's a bit of a hacky solution, but it'll make our movement feel a lot better. Now to do that, and we will do it here in our movement inputs, we're going to essentially stick the player to a specific point on the surface if you're not touching the movement controls, and if the movement of the player relative to the ground is, small enough that we want to just ignore that slight drift. So I'm going to call this variable should stick to surface. And it will be true if our movement is equal to 0, if the ground is not null, and if our relative velocity to the surface at our global position and with our linear velocity, if the length of that velocity is less than 0.2. So we will forcefully stick the player to a specific point on the surface if they are not trying to move, if they are on the ground, and if their relative speed to the planet is less than 0.2 meters per second. So if we should stick to the surface, well, first we want to track, 1, if we are already stuck to the surface, and 2, what position are we being stuck to. So we'll go back up here to the top, and we can define private bool is stuck to surface, and private vector3 surface position. So this is going to be the position relative to the surface that we're stuck to, and if we're stuck there or not. So now here we can say if we are stuck to the surface, then our global position is going to be equal to ground.toGlobal surface position. Otherwise, if we should be stuck to the surface and we are not already stuck, that means that we have just been stuck to it. So we will say is stuck to surface equals true, and we will record our current position, which is ground.toLocal global position. And the reason why, of course, we're converting from our global position to a local position, because even though we're staying still relative to the planet, we're still moving a lot relative to, the center of the solar system, because we're orbiting around the sun. If we're on the moon, we're orbiting around the Earth and the sun. So we convert this to a local position. However, when we set our global position, we have to just convert it back to global. And lastly, if we should not be stuck to the surface, we will set is stuck to surface equals false. And now if I go back into the game, we head back over to Australia, and you can see I'm no longer drifting, I'm no longer, spinning. Now let's see what happens if we go to the moon. Actually see that our rotation, trying to look up and down, is actually backwards. So I'll deal with that in a moment. But just to check that, yeah, standing on the surface of the moon now, we are, not drifting, we are not rotating in any way that we don't want to be, and that's working pretty good. So the only part that is broken here is our up and down rotation. So you can see that looks pretty wrong. Okay, yeah, I've looked over my previous code, and so the issue is that delta x here, this should be positive. However, here, this should be negative. And I believe that will correct the rotation. So we're here in space, I look down, yeah, and you can see my entire body is rotating to look down. I look up, my entire body rotates to look in that direction. Now if I hold R, oops, I got pulled in by the sun's gravity. I forgot that I was just standing still, essentially, in space. Okay, I've got us back up in space. Now if I hold on R, and this is me turning left and right, so you can see I'm turning around the forward-facing vector. And now that we've, had our camera out for that sanity check, we can just bring that back in to be... Okay, so there must be one last issue here with the camera rotation. That is a very stupid typo. This was the delta time. Should have been delta x. That's... yeah. Yeah, so with that fixed, now it actually works. And so that's the entire project done. Let me know in the comments if this was helpful, and give me any suggestions for what you'd want to see next. Okay, bye.